Welcome to ETHDam, to ETHDam, to ETHDam, to ETHDam, to ETHDam.
Hello everyone, my name is Vivian Plasencia and I'm a software engineer in the Privacy and Scaling Aspirations team at the Ethereum Foundation. And today I'm going to talk about scaling Semaphore. So let's start with what is Semaphore. Semaphore is a zero-knowledge protocol that allows users to prove their membership in a group and send messages such as votes or feedback without revealing their identity. This means that the messages are not linked to the identities, and Semaphore also provides a mechanism to prevent double signaling, which means that you cannot successfully verify the same proof twice. Semaphore works off-chain and on EVM-compatible chains, and right now it also works on Rust, so yeah. There are some use cases for Semaphore, and I'm going to mention a few of them. So there is Supas, the Supas project. It was used at DEF CON. It was used for ticketing for the event. And also the World project, which is for anonymous proof of that you are a real human. And also Pairwise, which is a project for anonymous voting. Here is a link to a list of projects, other projects using Semaphore, so you can check them out. The first commit for Semaphore was in 2019, and the first release was in 2020. And after that, there has been a new release almost every year, and the last release was version 4 in 2024, and that's the current one we have now. Semaphore version 4 introduces two new main features. One is related to the identity schema, and the other is related to the new Merkel tree, which is called Lean Incremental Merkel tree, which is an optimized incremental Merkel tree. The Semaphore identity is an EDDSA public-private key pair and also a commitment. Now, with these identities, you can generate signature, which is generate and verify signature, which is great. Right before, people used to use CKP, so now you can do it out of the box. The Lean Incremental Merkel tree is the new data structure we are using for the group operations. And this is an improvement over the incremental Merkel tree that was used in version 3. And this has two main improvements over the incremental Merkel tree used before. There are not zero hashes, no more zero hashes. This means that before, if there were, let's say, 3 members in the tree, we will create a zero hash for the 4th member so that the parent hash can be created. So now this is not needed anymore, since right now what is done is that the parent will have the same value as the child. If we won't create a new one to create the parent hash. And also the depth is dynamic now, which means that before, with the incremental Merkel tree, you needed to add a static depth, and let's say 20 or 30 now, it will grow over time, so it's dynamic, so it depends on the number of members will be the depth, and if there are more members, the depth will increase, but dynamically. You don't need to do it since the beginning. There is actually a paper about it. You can go to the CKKeep repo and read the paper. There are benchmarks. You can see like the algorithms. There are pseudocodes and everything. So please check them out if you are really interested in that. And this is an example of an incremental Merkel tree and a linear incremental Merkel tree. As you can see, the incremental Merkel tree will always have a power of 2 number of elements because of the zero hashes. It doesn't matter if you have 3, 4, 5 members. You will always have a power of 2 elements, and that's not the case for the linear incremental Merkel tree because it depends on the number of members and there are no more zero hashes. Here is a QR code with all the information related to the Semaphore version 4 research, all the data structures we were considering, and everything related to EDSA, why we decided these things, and everything. So go check it out if you are interested in this part. In the Semaphore documentation, there are some benchmarks for version 3 and version 4. And in general, as a summary, version 4 performs better than version 3. I'm going to talk about scaling Semaphore for mass adoption now. And right now, Semaphore is stable, it was audited, and it has always been audited. And it works well, it was used at DEF CON, and a lot of applications use it. But for thousands of users, it's fine, it will work on browser. But with millions of users, you will need to use the server because the browser won't be able to fetch all the members and recreate the tree and generate the proof because the tree will be big. And then your UI will become unresponsive if you do that. So a possible solution could be web workers, but it's still not a good user experience. So that's why we have been working on this, because since it's stable now, we can focus on mass adoption because it works. There are some key challenges for mass adoption when we were considering this, and one was the lack of cross-platform support. For example, there was no support on native mobile, StarNet, Stellar, or Cardano, and other ecosystems. And another was that we always want to make sure that proof generation and verification are as fast as possible. So we have been also doing some things in this for this point. And another thing is that to generate the proof, you need the Merkel proof. And in the UI, it was almost not possible because, as I was saying, for millions of members, you need to fetch all the members and then recreate the group. And it was not possible because it's the user, the UI. And I'm going to also talk about what we have been doing for this. First, we created the Semaphore version 4 specification document. We created this so that developers can easily implement Semaphore on other ecosystems, and they can also better understand the project. And you can check it out here in this QR code. Also, we implemented Semaphore Rust. The idea was to support native mobile, and now you can generate and verify Semaphore proofs with Rust, and also it's supported in mobiles. And now the Semaphore proofs are interoperable across JavaScript, Solidity, Rust, and native mobile. This was a collaboration with PSE Research and Mopro teams to create this implementation. There is also an ongoing research and development to optimize Semaphore regarding proof generation and verification using NOR. And this is a collaboration with Aztec and is being implemented by the HashCloud team. There are some interesting benchmarks. You can check them out in this QR code, in this link. And they have been optimizing the code, and they are also have been doing some research implementation with recursive proofs. So I'm very excited about the results. So I will be talking about it when we have more results. There is also an ongoing research and development to benchmark private information retrieval to have faster client-side Merkel proof generation. And this is a collaboration with the PSE research team. So there are some benchmarks now, and you can check more information about this in this QR code. And I will be talking about more benchmarks in the future when we have more benchmarks, but there are already interesting benchmarks so far. You can learn more about Semaphore on the website, documentation. You can also go to Telegram to ask questions or join the discussions there and check the GitHub. Thank you very much. And this is all my information. Thank you.